Hello there, and welcome to the Sleepy Science Channel. Tonight, we're drifting through the seasons, the quiet rhythms that govern our world. This slow dance of light and shadow reshapes everything we know. From the shimmer of summer heat to the frozen stillness of winter, each season rewrites the story of life in its own unique way. Across oceans, deserts, and forests, the same invisible rhythm moves beneath it all. It pulls the tides, guides the migrations, and paints the skies in patterns older than memory. The stars themselves sway to this rhythm. And even the air we breathe and our body's deepest cycles are affected by the seasons. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, just breathe. Let your eyes grow heavy, and let the rhythm of the seasons cradle your thoughts. Soft, endless, and eternal. Let's begin. Earth's seasons exist because its axis is tilted about 23.5 degrees. That small tilt is the hidden rhythm behind every pattern of warmth, cold, and light we know. Because Earth leans slightly as it travels around the sun, sunlight spreads unevenly over the planet through the year. In June, the northern hemisphere leans toward the sun, and the rays strike more directly, flooding it with heat and long days. 6 months later, the same regions cool as the sun sips lower in the sky. This simple geometry divides the year into seasons and sculpts the world's climates. Without that tilt, there would be no cycle of growth and rest, no spring thaw or autumn harvest. The slow turning of light across the planet governs the blooming of plants, the migrations of animals, and the rhythm of human life itself. Every calendar, every culture, and every moment of weather is a quiet echo of that cosmic lean. If that tilt disappeared, most of Earth would stay stuck in permanent spring or autumn. A planet spinning perfectly upright would feel frozen in time. The sun would rise and set at nearly the same spot every day. Day length would never change, and the concept of seasons would vanish. Regions near the equator would remain relentlessly warm, while the poles would exist in endless cold. Winds would weaken, rainfall would flatten into dull regularity, and storms would lose their power because the contrast between warm and cold air is what fuels them. Ecosystems would collapse under monotony. Crops would fail because they rely on changing light cues to flower and fruit. Animal migrations and breeding cycles would lose their timing signals. Life would persist, but with far less diversity and resilience. The tilt of Earth is not a minor detail of physics. It is the planetary heartbeat that keeps every living system pulsing, rising, and renewing with each turn around the sun. If the tilt increased, summers would scorch and winters would freeze entire continents. Even a few extra degrees of tilt would transform Earth into a planet of violent contrasts. The sun's path across the sky would swing higher in summer and sink lower in winter, exaggerating the difference between light and dark. Polar regions would face the sun directly for months, melting ice sheets and flooding coasts, only to plunge into deep darkness and extreme cold half a year later. The equator would be battered by shifting monsoons and unpredictable winds as the global heat balance flipped. Rainforests could dry into savannas, fertile farmlands might turn to desert. Civilization would struggle to adapt to a planet lurching between extremes. The tilt we have today is a fragile equilibrium between chaos and calm. Its stability allows oceans, forests, and climates to find a rhythm gentle enough for life to thrive, a narrow band of balance in a universe of wild possibilities. The moon stabilizes Earth's tilt without it. Seasons would swing wildly over millennia. The moon does far more than light our night sky. Its gravitational pull acts as an anchor that steadies Earth's wobble. Without it, our planet's axis could drift dramatically, swinging between nearly upright and steeply tilted positions over thousands of years. Such instability would send ice sheets and deserts migrating across the continents, shifting climate zones in ways that could erase ecosystems entirely. Mars, which lacks a large moon, already experiences this kind of chaos, with its poles tipping toward the sun and then away through the ages. The moon's steadying influence keeps Earth's tilt wobbling only a few degrees, creating long-term climate stability. Every spring and winter we know depends on this quiet partnership. The moon has shaped not only the tides, but the very predictability of the world we live in, making life's patterns possible across billions of years. Earth wobbles like a spinning top, slowly shifting its tilt every 41,000 years. Earth's axis is never perfectly still. It traces a slow and graceful movement called axial obliquity, in which the angle of the tilt changes by a few degrees over a cycle of 41,000 years. When the tilt grows steeper, the seasons intensify. Summers become hotter and winters colder. When the tilt lessens, they soften. This slow rhythm influences the spread of glaciers, the depth of oceans, and the rise and fall of ecosystems. Combined with other orbital cycles, it forms part of the Milankovitch patterns that guide Earth's long-term climate. Each change is gentle, almost imperceptible within a human lifetime. Yet over geological eras, it reshapes continents. The tilt we experience today is only one frame of a vast cosmic film where ice ages and interglacial periods come and go like the slow breathing of the planet itself. That ancient wobble has helped trigger ice ages throughout history. When Earth's tilt decreases, the difference between summer and winter weakens. Snow that falls in winter no longer melts fully in summer, gradually building layers of ice that reflect sunlight back into space. The more sunlight that bounces away, the colder the planet becomes, creating a feedback loop that plunges Earth into an ice age. When the tilt increases again, sunlight grows stronger and the ice retreats. Evidence of these cycles is etched into layers of rock, deep ocean sediments, and the air trapped in ancient ice cores. These records show that our world's climate has never been fixed. It swings gently between extremes, orchestrated by celestial geometry. Every cold gust of wind and every warm spring breeze is part of that vast pattern, where the quiet shifting of Earth's axis governs the rise and fall of entire ages. The equinox is a precise instant when the sun crosses Earth's equator. Though many think of the equinox as a full day, it is actually a single moment in time. At that instant, the sun's center aligns perfectly above the equator, and the planet's axis tilts neither toward nor away from it. Day and night appear nearly equal, but only briefly. This balance happens twice a year, in March and September, and has long been a symbol of harmony and renewal. Ancient observers built temples, pyramids, and calendars to mark the instant when light and dark matched. To stand under that equal sky is to feel a momentary symmetry rarely found in nature. The equinox reminds us that balance on Earth is always fleeting. Within hours, the planet's steady motion tilts again, and the long journey toward the next season quietly begins. Day and night are rarely perfectly equal on the equinox because of atmospheric refraction. The Earth's atmosphere bends light, allowing us to see the sun for several minutes before it actually rises and after it sets. This bending adds extra daylight, making the equal day slightly longer than the night almost everywhere on Earth. The degree of bending depends on air density, temperature, and elevation, meaning that the perfect balance of light and dark never truly happens for everyone at once. At the poles, where the sun lingers low on the horizon, the effect is even greater. The illusion of equality between day and night is poetic, not precise. Yet it is that illusion that gives the equinox its emotional weight. It is a reminder that what we experience as balance is often just the gentle distortion of light through air, an atmospheric kindness that lets the world glow a little longer before darkness falls. The word solstice comes from Latin for sea stands still. The solstice marks the point when the sun's path across the sky appears to stop moving north or south before reversing direction. For several days around this time, sunrise and sunset positions change so slowly that the sun seems to pause. The ancient Romans called it solstitium, meaning the standing still of the sun. The June solstice brings the longest day in the northern hemisphere, while December brings the shortest. Civilizations across history celebrated these turning points as moments of death and rebirth of light. Fires were lit, monuments aligned, and stories told of renewal and return. Even now, festivals and rituals continue in honor of that pause. The solstice is not just astronomy, it is humanity's oldest clock, a time when we feel most connected to the slow turning of the heavens above. The sun's apparent pause happens because its path across the sky stops moving north or south. Each day, the sun rises at a slightly different spot along the horizon as Earth orbits the sun. Near the solstice, that movement slows almost to a standstill. For a few days, the difference from one sunrise to the next is nearly impossible to notice. Then, slowly, the motion reverses, marking the return of the light's journey toward the opposite hemisphere. To early astronomers, this stillness was mystical proof that the sun itself could rest before beginning anew. Today, we know it as geometry and orbit, yet the feeling remains powerful. That brief pause in the sun's migration reminds us that even the grandest motions in nature include moments of calm. In that stillness lies the turning point of the year, when one season bows to the next and the cycle begins again. Ancient civilizations used solstices to mark the turning of the year and the rebirth of light. Long before mechanical clocks or written calendars, people looked to the heavens to measure time. The sun's path revealed the rhythm of life itself. When the days reached their shortest point, ancient observers noticed the light pause and then begin to return. That turning of the sun became the anchor for harvests, rituals, and myth. The winter solstice symbolized the death of darkness and the promise of renewal, while the summer solstice marked the peak of life and abundance. Fires were lit to call back the light, stones were raised to frame the dawn. Across Egypt, China, and the Americas, humanity found meaning in the same celestial moment. The solstices were more than seasonal markers. They were reminders that even the longest night gives way to dawn, that change is constant, and that the sun always keeps its promise to rise again. Stonehenge, Machu Picchu, and Chaco Canyon all align with solstice sunrises. Across continents and separated by millennia, civilizations built monuments that echoed the movement of the sun. At Stonehenge in England, the first rays of midsummer's dawn strike directly through the central stones, filling the monument's heart with light. In Peru, the builders of Machu Picchu carved sightlines so that the sun's rays at the winter solstice shine through a temple window and illuminate a sacred stone. In Chaco Canyon, New Mexico, spirals etched into cliffs mark the solstice with shafts of sunlight that pass through their centers for only a few moments each year. These structures were more than calendars. They were bridges between heaven and earth, showing that people everywhere felt the need to understand their place within the cosmos. Every alignment was an act of wonder, turning sunlight into architecture and time into something humans could touch. During the Northern Hemisphere's winter, Earth is actually closest to the sun. It feels backward, but it's true. Earth's orbit brings it nearest the Sun in early January, during the height of northern winter. The planet's path around the Sun is slightly oval, meaning the distance changes by about 5 million kilometers through the year. Yet this difference barely affects temperature. The warmth of a season depends not on distance, but on how directly sunlight strikes the surface. In January, the northern hemisphere is tilted away from the Sun, spreading its light thinly over a larger area, while the southern hemisphere faces the Sun more directly and enjoys summer. This asymmetry is the reason both hemispheres experience opposite seasons. Our orbit's closeness to the Sun does, however, make the southern hemisphere's summers slightly warmer and its winters milder. It is a small reminder that cosmic geometry, not proximity alone, decides how we feel the heat and cold of the year. The difference in distance to the Sun has almost no effect on temperature. The warmth of the seasons has almost nothing to do with how far we are from the Sun. The change in distance between the farthest and closest points of Earth's orbit is only about 3%, far too small to cause the dramatic difference between summer and winter. Instead, temperature is governed by the angle of sunlight and the length of the day. When sunlight hits the ground more directly, its energy concentrates and the air warms. When it arrives at a shallow angle, that energy spreads thinly, producing cooler temperatures. Earth's atmosphere, oceans, and land all respond to these angles, storing and releasing heat over time. This is why seasons vary far more by latitude than by distance. The illusion of warmth from proximity reminds us that what truly changes with the seasons is not how close we are to the Sun, but how the Sun touches us. Seasons are driven by sunlight angle, not proximity to the Sun. When the Sun sits high overhead, its rays strike Earth's surface directly, concentrating energy and warmth. When it sits low on the horizon, those rays must pass through more atmosphere and spread over a wider area, softening the heat. This simple change in geometry defines the seasons. In summer, long days and steep sunlight intensify warmth, while in winter, short days and slanted light chill the ground. Even at the same distance from the Sun, one hemisphere can bask in heat, while the other freezes. The shifting angle of sunlight drives weather patterns, ocean currents, and the migration of countless species. It also influences how plants capture energy, timing their growth to the changing path of the Sun. The tilt of the planet turns light into rhythm, translating celestial motion into the daily experience of heat, shadow, and renewal. The Arctic Circle marks where the Sun never sets on the summer solstice. At the top of the world, there comes a day when the Sun refuses to set. North of the Arctic Circle, the summer solstice brings 24 hours of daylight, an unbroken glow circling the horizon. The Sun drifts low in the sky but never dips below it, bathing tundra and ice in soft, perpetual light. This phenomenon, known as the midnight sun, transforms entire ecosystems. Plants photosynthesize without rest, birds nest and feed in constant brightness, and animals adapt their internal clocks to a world without night. For humans, the experience is equally strange. Time feels suspended, and sleep comes reluctantly. The same geometry that brings endless day also brings endless night 6 months later, when the Sun vanishes for weeks. In both extremes lies the power of tilt and orbit, shaping worlds that feel almost alien, yet belong entirely to our planet. The Antarctic Circle marks where the Sun never rises on the winter solstice. At the opposite pole, winter brings a season of darkness. South of the Antarctic Circle, the Sun disappears below the horizon for weeks or months, leaving the landscape in twilight and shadow. During this long night, temperatures plunge, winds howl, and the sea freezes into vast plates of ice. Yet even in this harsh stillness, life endures. Penguins huddle for warmth, seals rest on the frozen surface, and microscopic algae bloom beneath the ice where faint light filters through. When the sun finally returns, it rises with a low golden arc, transforming the entire horizon into a glowing ribbon. The Antarctic night and day are opposite reflections of the Arctic, created by the same celestial tilt. These cycles remind us that even the darkest season holds light in waiting, and that life adapts to extremes that seem beyond endurance. In Antarctica's midnight sun, temperatures can stay below freezing even under 24 hours of daylight. Constant sunlight does not guarantee warmth. Even when the sun circles the horizon all day, its rays strike the surface at such a shallow angle that little heat penetrates. Much of the energy reflects off the bright snow and ice, which act like mirrors. The air remains dry and thin, allowing heat to escape quickly into space. As a result, Antarctic summers can remain brutally cold despite perpetual day. Scientists working there experience an eerie contradiction: dazzling light, endless visibility, and biting cold that never relents. The landscape glows under the low sun, but the warmth never arrives. This combination of brightness and chill shows how the angle of sunlight matters more than its duration. In Antarctica, time seems frozen in both senses of the word, a world where the sun never sets, yet summer never truly comes. Near the equator, sunlight changes so little that seasons are defined by rainfall instead of temperature. In equatorial regions, the sun's path barely shifts throughout the year. Day and night remain nearly equal, and temperatures hover within the same narrow range. Instead of spring, summer, autumn, and winter, the cycle of life is measured by water, wet and dry seasons that alternate as air currents shift. When warm air rises and draws moisture from the oceans, rain pours daily in powerful bursts. When the air cools and sinks, skies clear and landscapes dry. These transitions control flowering, fruiting, and migration just as surely as temperature does elsewhere. Forests respond to the rhythm of moisture, not the tilt of the planet. In the heart of the tropics, the only seasons are those of the sky's generosity, the season of giving rain and the season of holding it back, both vital, both endlessly repeating. Monsoon seasons are caused by land heating faster than nearby oceans. When the sun moves overhead during summer, continents warm more quickly than the surrounding seas. The hot air above the land rises, creating a low-pressure zone that pulls in cooler, moisture-laden air from the ocean. As that air rises over the land, it cools and releases its water as torrential rain. This is the monsoon, one of Earth's most dramatic seasonal systems. In winter, the pattern reverses. The land cools faster than the sea, and dry winds blow outward, ending the rains. The entire process depends on sunlight, geography, and the slow breathing of the planet's atmosphere. For billions of people, the monsoon defines the rhythm of life. It brings both abundance and risk, nurturing crops and shaping civilizations while testing their endurance. The monsoon is the living dialogue between land, sea, and sky, repeating its vast conversation every year. The word monsoon comes from an Arabic word meaning season. The term has ancient roots. Traders along the Indian Ocean learned to read the changing winds that carried ships east and west with clock-like precision. They called these shifts mausim, meaning season, because the pattern was so reliable it became the foundation of navigation and commerce. Every year, merchants timed their voyages to the turning of the winds, bringing spices, gold, and knowledge between Africa, Arabia, and Asia. Long before meteorology, people recognized that the atmosphere itself has a heartbeat, a repeating pulse of heat and pressure tied to the movement of the sun. The legacy of that word endures. In every use of monsoon, we still speak of the connection between time, weather, and human survival. It is a reminder that our understanding of the seasons began not in laboratories, but on the decks of ships watching the horizon change with the wind. Some regions have only two seasons, wet and dry. In many tropical regions, the classic four-season calendar simply does not apply. Instead, life turns on a simpler axis, the arrival and retreat of rain. The wet season transforms the land with floods, lush growth, and humidity so thick it feels alive. Rivers swell, insects thrive, and forests hum with energy. Months later, the dry season arrives, draining the water and paring life back to its essentials. Trees drop leaves to conserve moisture, animals migrate, and humans plan harvests and travel according to these predictable swings. These two halves of the year shape every heartbeat of the ecosystem. They are reminders that seasons are not universal, but local, tailored to each landscape's dialogue with the sun and the air. For much of the world, the passage of time is not marked by temperature, but by the sound of rain returning to the earth. Tropical rainforests stay green all year but still follow invisible seasonal patterns in humidity and insects. At first glance, equatorial forests seem timeless. Leaves stay lush, birds sing constantly, and the air always hangs heavy with warmth. Yet hidden within this apparent permanence are delicate seasonal shifts. Tiny variations in rainfall and humidity change which flowers bloom and which insects emerge. Many trees drop fruit or release seeds only when humidity peaks, ensuring that their offspring have the moisture needed to survive. In turn, animals adjust their behavior to these subtle cues. Birds time nesting to match caterpillar surges. Frogs call louder after the first deep rains. Even microbial activity in the soil rises and falls with the hidden rhythm of the atmosphere. The rainforest seasons are written not in temperature or color, but in scent, sound, and moisture. It is a continuous cycle of change disguised as stillness, life dancing to a rhythm that only the forest itself can hear. In the Amazon, trees flower and fruit at different times depending on light levels, not heat. The Amazon basin stays warm year-round, yet its trees do not all bloom together. Many species measure the shifting angle of sunlight rather than temperature to decide when to flower or bear fruit. As the sun climbs higher or dips lower, it changes the way light filters through the dense canopy. Some trees bloom during the brightest months when sunlight pierces deep into the forest, while others choose dimmer seasons to avoid competition. This staggering of timing spreads food availability for animals and helps maintain biodiversity. Pollinators, from bats to bees, follow these botanical calendars as faithfully as the trees themselves. The forest breathes in patterns that seem chaotic, but are precisely tuned to light. Even in a world without winter, the sun's slow movement across the sky still directs the heartbeat of life hidden beneath the leaves. Coral reefs spawn during seasonal full moons when ocean temperature peaks. Corals live in environments where change is subtle, yet they rely on perfect timing. Once a year, often within a few nights of a full moon, corals across entire reefs release clouds of eggs and sperm into the water simultaneously. This synchronized event, triggered by seasonal shifts in temperature and moonlight, turns the ocean into a glowing snowstorm of life. The timing ensures that currents, tides, and light all align for maximum survival. Fish and plankton gather to feed, and the reef becomes a frenzy of motion. Scientists studying these events call them the heartbeat of the reef. a reminder that even under the sea, life runs on celestial schedules. The coral's quiet awareness of season and moon links the rhythms of ocean, earth, and sky in one of the planet's most intricate dances. Seasonal winds shape sand dunes across entire continents. Deserts may look still, but they move constantly under the influence of wind. As seasons change, prevailing winds shift direction and strength, sculpting dunes into flowing forms that migrate over time. In some regions, the wind reverses completely between summer and winter, reshaping the same dunes again and again. Each grain of sand traces a journey hundreds of kilometers long, carried by air currents born from the sun's uneven heating of the land. The patterns left behind, crescents, ridges, and star-shaped peaks, are records of atmospheric rhythm written in sand. Satellites have tracked dunes that move several meters each year, showing that even the driest landscapes pulse with motion. Deserts breathe in their own slow language, shaped by the invisible hand of seasonal wind. The jet stream shifts position with the seasons, steering storms around the world. High above Earth's surface, powerful rivers of air race around the planet, guiding weather patterns like invisible highways. These jet streams form where warm tropical air meets cold polar air, and their positions drift north and south as the seasons change. In summer, the jets retreat toward the poles. In winter, they slide closer to the equator, carrying storms and cold fronts with them. This shifting flow affects everything from rainfall in Africa to hurricanes in the Atlantic. Air travel, ocean currents, and even agriculture depend on its moods. When the jet stream becomes unstable, heat waves, droughts, or blizzards can linger far longer than usual. Though we cannot see it, this upper air current is the silent conductor of the planet's weather, weaving the energy of the seasons into the patterns we feel below. Migrating birds use the sun's seasonal path to navigate thousands of miles. Birds crossing continents follow routes more precise than any map. Many species watch the sun's position in the sky to orient themselves during migration. As daylight lengthens or shortens, it signals when to begin their journeys. They memorize the arc of the sun relative to the horizon and adjust their course as its angle changes with latitude. Some even combine this solar map with magnetic sensing to find their way across oceans and deserts. The result is a navigational system of extraordinary accuracy, guided entirely by light. For these travelers, the changing seasons are not just background weather, but the very mechanism of direction. The same tilt that shapes our climate also paints pathways through the sky, allowing wings to trace the curve of the Earth from one hemisphere to the other and back again each year. Some whales follow seasonal food blooms across hemispheres. In the vastness of the ocean, whales live by the seasons just as creatures on land do. As sunlight changes through the year, plankton blooms erupt in the world's temperate seas, attracting swarms of fish and krill. Baleen whales migrate thousands of kilometers to feed in these rich waters during the summer months, then travel back toward the tropics to breed in warmer, safer seas during winter. Their migrations follow invisible corridors shaped by sunlight, temperature, and food availability. Each journey is a response to the same celestial rhythm that drives the tilt of Earth. The lives of whales, synchronized with the pulse of the planet, connect polar oceans and equatorial lagoons in one endless seasonal circuit of birth, feeding, and return. The Arctic tern experiences 2 summers each year by chasing daylight around the globe. Few creatures follow the seasons more completely than the Arctic tern. This small bird travels from the Arctic to the Antarctic and back again every year, tracing a path that can exceed 70,000 kilometers. By flying between hemispheres, it lives in near-continuous daylight, experiencing 2 summers annually. The journey allows it to feed on the endless abundance of polar waters at both ends of the Earth. Scientists tracking these birds with miniature transmitters discovered that terns often zigzag across oceans to ride favorable winds, turning migration into a finely tuned art. Over a lifetime, one tern may travel the equivalent distance to the moon and back several times. Its path is a living loop of light, proof that even a creature weighing less than a smartphone can master the geometry of the seasons better than any human-made clock. Bears time their hibernation with the shortening of daylight, not cold alone. Bears do not wait for snow to fall before retreating into their dens. Their internal clocks run on light, not frost. As autumn arrives, the decreasing daylight triggers hormonal changes that slow metabolism and increase hunger. The bears begin feeding relentlessly, doubling their weight on berries, roots, and fish. When the nights stretch long enough, they stop eating and begin to sleep. Inside their dens, body temperature drops, breathing slows, and heartbeats become faint. Mothers give birth in midwinter while still in this half-suspended state, nursing tiny cubs against their warmth. When spring light returns, their bodies respond once again, waking slowly as the world thaws. This delicate synchronization between light and biology ensures survival in some of Earth's harshest climates. Their hibernation is not an escape from cold, but an instinctive partnership with the shifting rhythm of sunlight. Monarch butterflies migrate to stay in endless spring. Each year, monarch butterflies perform a migration so vast that no single generation survives the entire journey. They begin in the northern United States and Canada, flying southward toward mountain forests in Mexico, where they cluster by the millions on fir trees through the winter. Months later, their descendants travel north again. These fragile creatures navigate using the angle of the sun and the pull of Earth's magnetic field. Their journey ensures that they remain within mild spring-like conditions throughout the year, avoiding both frost and extreme heat. Along the way, they pollinate countless plants, forming a living bridge between climates and ecosystems. Scientists still marvel at how creatures so light and short-lived can navigate so precisely across continents they have never seen before. Theirs is a biological relay, each generation carrying a fragment of memory passed through instinct, tracing sunlight's path across a hemisphere. Deciduous trees sense the length of night to know when to drop their leaves. The shedding of leaves each autumn is a carefully timed survival strategy. Trees monitor the length of night through specialized pigments in their leaves that react to light. When the nights grow longer than a critical threshold, the trees begin withdrawing nutrients from their leaves and storing them in their roots. This process seals off each leaf with a layer of cells that eventually causes it to fall away. The change in daylight acts as a universal signal, unaffected by brief cold snaps or warm spells. By the time winter arrives, the trees stand bare but alive, conserving water and energy for the next growing season. When daylight lengthens again in spring, new buds form at the same rhythm. The trees' seasonal awareness ensures that their cycles of growth and rest remain perfectly synchronized with the movement of the sun. The color of autumn leaves depends on chemistry that varies by species and sunlight. The transformation of green forests into shades of gold, red, and purple is the result of complex chemistry within each leaf. When chlorophyll breaks down, it reveals pigments that were present all along. Carotenoids produce yellow and orange hues, while anthocyanins create the vivid reds and purples that define the season. Each tree species has its own chemical balance, shaped by sunlight, temperature, and genetics. Cool nights intensify the red pigments, while overcast days produce more subdued tones. Maples burn crimson, birches turn bright gold, and oaks fade into deep brown because their cells produce different molecular compounds. The variation is so precise that scientists can identify tree species by analyzing pigment ratios under a microscope. The colors of autumn are not random beauty. They are a chemical conversation between trees and light, unfolding across billions of leaves in perfect synchrony. Cool nights and bright days create the most vivid fall colors. The most spectacular autumn landscapes occur when the weather strikes a delicate balance. Warm, sunny days keep trees photosynthesizing, filling their leaves with sugars. Cold nights slow the movement of those sugars out of the leaves, triggering the production of red and purple pigments. Too much warmth, and the color fades. Too much cold, and frost kills the leaves before they can change. The clearest skies produce the brightest hues because sunlight fuels pigment creation while revealing every shade. This is why mountain regions with crisp, dry autumns glow so vividly. Each season's colors tell a story about that year's weather, written in the chemistry of every forest. The pattern repeats endlessly, yet never looks the same twice. Each autumn a unique collaboration between light, temperature, and time. Some trees delay leaf fall to capture a few extra hours of light each day. Not all trees surrender their leaves when their neighbors do. Oaks, beeches, and some hornbeams often keep their withered leaves through winter, a phenomenon called marcescence. The reason lies in small advantages gained from clinging to light. By delaying the drop, these trees continue photosynthesizing, even as the days shorten, drawing in the last bits of energy before deep cold sets in. The dry leaves may also serve other purposes, shielding buds from frost, deterring grazing animals, or capturing snow that melts slowly into the soil. When spring arrives, new growth pushes the old leaves away. The persistence of marcescent trees shows how finely evolution tunes every response to the environment. Even the timing of a single leaf's fall is part of the planet's intricate negotiation between sunlight, temperature, and life. The scent of autumn comes from microbes breaking down fallen leaves. When forests fill the air with that unmistakable earthy smell, it is not the trees themselves you are sensing, but the work of billions of microbes. After leaves fall, bacteria and fungi begin decomposing them, releasing molecules like geosmin and petrichor that mix with moisture in the air. These compounds are incredibly potent, detectable by the human nose in concentrations of just a few parts per trillion. The scent signals that nutrients are returning to the soil and that ecosystems are recycling the sunlight captured months before. It is the aroma of decay, but also of renewal. Every breath of cool autumn air carries the chemical memory of summer forests transforming into fertile ground. In that faint, sweet musk lies the promise that life will rise again from its own remains when the light returns. Spring begins when the sun moves north of the celestial equator. The moment that marks the start of spring is not a date chosen by humans, but a point in Earth's orbit. At the vernal equinox, the sun's center crosses directly over the celestial equator, and the length of day and night become nearly equal across the globe. From that instant forward, daylight begins to increase in the northern hemisphere. Plants awaken from dormancy, animals emerge, and the tilt of Earth brings warmth back to the land. The equinox has guided agricultural calendars and cultural rituals for millennia, from ancient Persia's Nowruz to the balancing of eggs in folklore. Though invisible to the eye, this astronomical crossing defines the rhythm of life on the planet. Each spring, as sunlight stretches northward again, the world answers the same timeless signal: to grow, to move, and to begin again. Early flowers sense soil temperature deep below the surface to time their bloom. Beneath frozen ground, the earliest flowers wait for subtle signs of change. Long before air temperatures rise, heat begins to penetrate the soil. Many species, like snowdrops and crocuses, have evolved root sensors that respond to the gradual warming deep below the frost line. These signals trigger biochemical changes that prepare the plant to grow, even while ice may still linger above. Emerging early gives these flowers a crucial advantage. They can bloom before taller plants block the light and before most insects awaken. Their petals provide the first food for bees and other pollinators. In this way, even the smallest blossoms help restart entire ecosystems each spring. Their precision is extraordinary, a silent calibration between the Earth's slow warming and the pulse of life ready to rise again. Many plants measure night length through pigment molecules called phytochromes. Plants keep track of time not through vision, but through chemistry. Inside their cells, pigment molecules called phytochromes act as natural clocks, shifting shape depending on how long they are exposed to light. During long nights, these molecules accumulate in one form during bright days. They transform into another. By comparing the balance between the two, plants can determine how long the night lasts, and therefore what season it is. This process governs when flowers bloom, seeds germinate, and leaves fall. Short nights tell summer crops to grow rapidly, while long nights cue others to rest. The system is so precise that artificial lights can confuse plants, altering their growth cycles. Every field, forest, and garden depends on this invisible conversation between sunlight and pigment, where each sunrise resets the biological calendar of life on Earth. Grass grows faster in spring because sunlight triggers nitrogen cycles in soil. As spring sunlight strengthens, it warms the ground and reawakens soil microbes. These microorganisms begin breaking down organic matter, releasing nitrogen compounds that plants can absorb. The process, called mineralization, accelerates rapidly when temperatures and light levels rise together. Grasses respond instantly, drawing up nitrates to build new cells and pushing out vibrant green shoots. The effect is visible across entire landscapes. Hills that were dull and brown in winter turn luminous within days. Rainfall helps distribute nutrients deeper into the roots, fueling the surge of life that defines the season. The pattern repeats each year like clockwork. Sunlight stirs bacteria. Bacteria feed grass, and grass feeds the entire chain of grazing animals that depend on it. The greening of the earth each spring begins not in the sky, but in the microscopic work beneath our feet. Bees emerge in synchrony with seasonal blooms they've evolved to match. Bees and flowering plants have spent millions of years adapting to each other's rhythms. Many bee species remain dormant through winter, waiting until the first blossoms open. The timing is no coincidence. It is locked into the changing temperature and length of daylight that both organisms share. When spring arrives, warming air releases floral scents that signal nectar is ready. Bees respond, their internal clocks tuned to the same cycles of sunlight that guide the plants. Each pollination event sustains the next generation of both species, ensuring survival through mutual precision. If climate shifts cause the flowers to bloom too early or too late, entire ecosystems can falter. The hum of bees drifting through spring air is more than sound. It is the harmony of two forms of life keeping perfect time with the turning of the year. Some frogs thaw from solid ice when spring sunlight returns. In the northern forests, wood frogs endure winter as living ice. Their hearts stop, blood freezes, and their bodies turn rigid. They survive this suspended state because glucose and urea flood their cells, preventing ice crystals from rupturing tissues. For months, they lie buried under snow and leaves, appearing lifeless. When spring sunlight warms the ground, they thaw slowly, heartbeat returning first, then movement, then breathe. Within days, they gather in meltwater pools to call and breed. This freeze and thaw miracle allows them to live farther north than almost any other amphibian. Their entire existence depends on the season's rhythm, on the cold that stops time and the warmth that restarts it. Each spring, the forest resonates with their voices, proof that life can persist even after months locked in ice. Seasonal changes in daylight affect hormone levels in nearly all animals. Light acts as the master signal for animal biology. When sunlight enters the eyes, it travels through neural pathways to the brain's pineal gland, altering production of the hormone melatonin. Long days reduce melatonin levels, promoting wakefulness, activity, and breeding behavior. Short days increase it, triggering rest, migration, or hibernation. The same pattern appears across mammals, birds, fish, and even humans. In temperate regions, animals rely on these shifts to prepare for seasonal challenges, storing fat, growing thicker coats, or changing color. The body's chemistry flows in step with the sky's changing light. Even artificial illumination can disrupt these natural cycles, confusing migration routes and sleep patterns. The alternation between long days and long nights is more than atmosphere. It is the hormonal heartbeat of the biosphere, a clock that has kept perfect time since life began. Human mood and sleep patterns subtly follow seasonal light cycles. Though we live under electric light, our bodies still obey the rhythm of the sun. As winter shortens the days, melatonin production increases, leading many to feel drowsy earlier in the evening. Serotonin levels can also dip, influencing mood and energy. In spring and summer, longer daylight reduces melatonin, improving alertness and lifting spirits. Circadian clocks in every cell respond to these seasonal changes in illumination, adjusting hormone release, body temperature, and metabolism. Some cultures once scheduled festivals of light around the darkest times of the year to counterbalance this natural ebb. Even now, exposure to morning sunlight helps restore energy and regulate sleep patterns. Humans may have insulated themselves from nature's cycles, but our biology never truly forgets them. Every sunrise still resets the internal rhythm we share with every other living thing that feels the turning of the seasons. The smell of spring rain comes from bacteria releasing spores after dry months. That distinctive scent rising from the earth after the first rain of spring is created by living chemistry. During dry periods, soil bacteria called actinomycetes form hardy spores that lie dormant in the dust. When rain finally arrives, falling droplets dislodge these spores and release a compound called geosmin into the air. Humans are extraordinarily sensitive to geosmin, able to detect it at concentrations of just a few parts per trillion. It is the aroma of renewal, signaling that moisture has returned and life can begin to grow again. The smell's emotional power runs deep because it has accompanied every rebirth of vegetation for millions of years. Each breath after a fresh rain carries the microscopic evidence that the long sleep of winter has ended and the living world is stirring awake once more. In summer, lightning strikes the Earth about 8 million times per day. During summer, the planet's atmosphere becomes a global engine of energy. Warm air rises rapidly, forming towering cumulonimbus clouds that churn with electrical charge. Collisions between ice particles and droplets separate positive and negative charges until the tension releases in a flash. Each lightning bolt travels faster than the human eye can follow, heating the air to tens of thousands of degrees and producing a shockwave we hear as thunder. About 8 million of these discharges occur every day across the planet, connecting sky and ground in brief, brilliant contact. Beyond their drama, lightning bolts play an essential role in chemistry, splitting nitrogen molecules that later fall as fertilizer in rain. They are the spark of renewal as much as destruction, natural electricity maintaining the balance between energy, air, and life. Warm air in summer holds far more water vapor than winter air. The ability of air to hold moisture depends entirely on temperature. As air warms, its capacity to contain water vapor increases exponentially. This is why summer feels humid, while winter feels dry, even at similar humidity percentages. When warm air rises, it carries moisture upward until cooling forces condensation into clouds and rain. The process stores and releases enormous amounts of energy, driving weather patterns across the globe. In tropical regions, this cycle fuels the daily rhythm of rainfall, while in temperate zones, it feeds thunderstorms and summer showers. The heavy, damp sensation of midsummer air is the atmosphere at full capacity, a living reservoir of potential rain. When temperatures drop again, that same vapor vanishes and the sky clears. The invisible chemistry of humidity links temperature, pressure, and sunlight in a seamless cycle that defines each season's character. Summer thunderstorms help redistribute heat from the equator toward the poles. Every thunderstorm is part of a global mechanism that balances heat. The equator receives far more solar energy than the poles, creating a constant need for redistribution. As warm, moist air rises in tropical regions, it cools and releases heat high in the atmosphere, where fast-moving winds can carry it thousands of kilometers. Each storm transfers energy upward and outward, reducing temperature contrasts across the planet. Without this process, tropical regions would grow ever hotter, while polar zones froze harder. The rumble of thunder is the sound of equilibrium being restored. Even violent storms serve a purpose, helping to keep Earth's climate stable over the long term. The same electrical towers that light the summer sky are the planet's way of breathing, sending warmth from crowded latitudes to places where the sun barely touches the ground. Ocean currents shift seasonally, influencing weather patterns worldwide. The great conveyor belts of the sea are not constant. As winds change with the seasons, ocean currents respond, altering the flow of warm and cold water around the globe. In summer, trade winds intensify in some regions, strengthening surface currents that transport heat north or south. In winter, those winds weaken or reverse, allowing cooler, deeper water to rise. These shifting currents determine rainfall, temperature, and storm tracks on every continent. The monsoons of Asia, the hurricanes of the Atlantic, and even the mild winters of Europe all depend on how the oceans circulate energy through the year. The sea's slow seasonal breathing regulates the planet's climate far more than any local weather event. To watch a wave roll ashore is to see the distant heartbeat of the seasons themselves, carried across thousands of miles of moving water. The El Niño and La Niña cycles reshape global seasons every few years. Every few years, the Pacific Ocean shifts its pattern of heat, altering weather across the entire planet. When surface waters near South America grow unusually warm, the pattern known as El Niño begins. This warmth changes wind direction and weakens upwelling currents, reducing nutrients for marine life. Meanwhile, distant regions feel its reach. Floods in some places, droughts in others, disrupted monsoons, and altered storm seasons. Eventually, the ocean flips to the opposite phase, La Niña, when cooler than normal waters strengthen trade winds and enhance rainfall in the Western Pacific. Together, these alternating patterns act as the planet's climate heartbeat, rising and falling on cycles that can last 2 to 7 years. They influence harvests, coral growth, fisheries, and even the strength of hurricanes. Though driven by a single ocean basin, their echoes ripple across every continent, reminding us that all weather is ultimately connected. Ice sheets grow and shrink slightly each year with the seasonal tilt of sunlight. Even in stable climates, the world's great ice sheets are never still. As sunlight waxes and wanes through the year, the edges of Greenland and Antarctica breathe in slow rhythm. expanding in winter and retreating in summer. When sunlight strikes at a lower angle, less heat reaches the surface, allowing snow to accumulate faster than it melts. As the planet tilts back towards summer, the balance reverses. Satellite measurements show these changes happening every year, revealing ice fronts that advance and withdraw like tidal waves of frozen water. Though the total volume remains relatively steady over short timescales, the process influences sea level, ocean salinity, and weather far beyond the poles. The annual pulse of the ice reminds scientists that even the coldest parts of Earth are dynamic, responding continuously to the dance of sunlight and shadow. Snow reflects up to 90% of incoming sunlight, cooling the planet further. Fresh snow is one of nature's brightest mirrors. Its white surface reflects most of the sunlight that hits it, bouncing energy back into space and preventing the ground beneath from warming. This property, called albedo, helps regulate Earth's temperature. As snow cover spreads in winter, more sunlight is reflected, reinforcing the cold. When the snow melts, darker surfaces absorb heat again, triggering the next seasonal shift. This feedback loop has enormous influence on climate stability. Regions with long-lasting snow, like the Arctic and mountain ranges, act as natural thermostats for the planet. When snow cover decreases, even slightly, global temperatures rise faster because more solar energy is absorbed instead of reflected. Every glittering field of snow plays a quiet role in the balance of the world's energy, tiny crystals, each catching sunlight, keeping the planet from overheating. The first snow of winter can form from dust, pollen, or volcanic ash high in the sky. Each snowflake begins as a microscopic particle floating in the atmosphere. Water vapor condenses around it, freezing layer by layer into intricate crystals. The first snows of winter often form around unusual seeds, grains of dust swept from deserts, bits of pollen carried on the wind, or even volcanic ash from eruptions half a world away. These tiny fragments act as nuclei for ice, giving shape to the flakes that eventually drift down through the clouds. The type of particle influences how the snow crystal forms: plates, needles, or branching stars. Once on the ground, they record a trace of their origin, meaning that a single flake falling in Europe might contain dust from the Sahara. The first snow is therefore both local and global, a union of earth and sky formed from the smallest pieces of matter suspended in the air. Polar bears hunt most successfully during the frozen season, then fast all summer. The life of a polar bear follows the rhythm of ice. In winter, when the Arctic Ocean freezes, the bears roam across the solid surface to hunt seals that surface through breathing holes. Each successful hunt builds fat reserves that will sustain them through the lean months ahead. When summer arrives and the ice retreats, they lose access to their prey. Many drift on remaining floes or move to land, fasting for weeks or months while living off stored energy. This seasonal pattern is so finely tuned that even small changes in ice formation can affect their survival. As warming temperatures shorten the frozen season, bears must travel farther and burn more energy to find food. Their entire existence is bound to the heartbeat of freeze and thaw, a life written in the shifting boundaries between solid and sea. Sea ice forms patterns that reveal wind direction during each season. From orbit, the frozen surface of the polar oceans appears etched with vast swirling lines. These patterns trace the movement of wind and current across the ice. When strong winds push in one direction, sheets of ice fracture and collide, forming ridges that rise above the surface. During calmer seasons, thin new ice called fryzl forms in smooth, glassy sheets that drift quietly. Scientists can read these markings like a map, interpreting the forces that shaped them and the season in which they formed. In spring, melt ponds scatter across the surface, reflecting turquoise light. while in autumn, the same areas freeze again into darker tones. The surface of the sea ice is a living record of motion, a constantly rewritten story of temperature, wind, and water that reveals how the atmosphere and ocean interact from year to year. Some fish change color, or even sex, depending on the season. Seasonal cycles can reshape not only landscapes but living bodies. In many fish species, changing light and temperature trigger transformations in color, pattern, and sometimes even sex. Coral reef fish often brighten their hues during breeding seasons to attract mates, while Arctic species darken as ice retreats to blend with the seafloor. Certain wrasses and groupers can switch from female to male when the breeding season begins, ensuring that reproduction continues efficiently. These changes are driven by hormones responding to seasonal light and temperature cues. In colder months, metabolism slows, colors fade, and activity decreases. When warmth returns, the same biological signals reverse. The underwater world shifts palate and behavior as predictably as forests do in autumn. Every creature attuned to the planetary rhythm that dictates when to feed, when to rest, and when to transform. The northern lights peak during equinox months, when Earth's magnetic field is most aligned. The aurora is not constant. Its displays strengthen and fade through the year, reaching their greatest intensity around the equinoxes. This timing occurs because Earth's magnetic field tilts relative to the incoming solar wind, aligning most efficiently in March and September. When streams of charged particles from the Sun collide with atoms in the upper atmosphere, they create curtains of colored light. During equinox months, the alignment allows more of these particles to funnel toward the poles, igniting the sky in green, violet, and crimson. These displays are so powerful they can be seen from space, tracing luminous rings around the planet's magnetic poles. The link between the aurora and the seasons is a reminder that even light in the night sky moves to Earth's rhythm, guided by invisible geometry between the sun, the atmosphere, and our tilted world. Many cultures base their calendars on solstices and equinoxes instead of months. Before mechanical clocks, time itself was measured by the sky. Civilizations across the world built calendars around the 4 pivotal points of the solar year, the solstices and equinoxes. These events divided the year into natural quarters, marking the extremes of light and balance. Agricultural societies relied on them to predict planting and harvest times, while spiritual traditions wove them into stories of birth, death, and renewal. Temples in Egypt, Mesoamerica, and Asia were constructed so sunlight would illuminate their chambers precisely on these days, turning architecture into astronomical instruments. Even today, many calendars, from Persian to Hindu to Chinese, still align holidays and New Years with these celestial milestones. To track the seasons was to understand both survival and meaning. The sun's movement across the sky gave humanity its first universal language of time. The earliest known calendar in Scotland tracked lunar months aligned with seasonal sunlight. Archaeologists in Scotland uncovered a field of ancient pits dating back nearly 10,000 years, a calendar older than writing. The pits were arranged in an arc that mirrored the lunar cycle, tracking the waxing and waning of the moon. What makes it remarkable is that the alignment also corresponded with the rising sun at the winter solstice, suggesting that its builders synchronized lunar months with seasonal sunlight. This dual system helped hunters and gatherers predict migrations, plant growth, and the return of key animals. The discovery shows that even before agriculture, people were observing the interplay between moon, sun, and Earth's tilt. The alignment of these pits across millennia reveals an early understanding of celestial rhythm, a calendar not carved in stone, but in the soil of time itself. Ancient farmers planted and harvested by the shadow length of stones and poles. Before modern calendars, Early farmers relied on simple tools to mark the progress of the seasons. By watching the length and direction of shadows cast by standing stones, poles, or even trees, they could determine when the sun had reached critical points in the year. As days lengthened, shadows shortened. As winter returned, they stretched again. By noting when shadows reached certain positions, farmers knew when to plant seeds or prepare for harvest. These primitive observatories were astonishingly accurate, serving as both sundials and seasonal compasses. Some of the oldest agricultural sites show alignments that match the solstices exactly. Over generations, these shadow measurements evolved into formal calendars, the foundation of all organized civilization. Each moving shadow told a story of sunlight and time, a reminder that the first clocks were made of light itself. The Egyptian calendar began with the annual flooding season of the Nile. In ancient Egypt, the rhythm of life depended on the river. Every year, the Nile overflowed its banks, leaving behind fertile silt that renewed the farmlands. The Egyptians realized this event coincided with the rising of the star Sirius at dawn, just before the summer solstice. They built their calendar around that observation, dividing the year into 3 seasons: Afet, the flooding period; the growing, and Shemu, the harvest. Each season contained 4 months of 30 days. This system linked celestial events directly to agricultural cycles, binding heaven and earth in a predictable pattern. The Nile's flooding was not chaos but order, a seasonal pulse so regular that it became the backbone of one of history's greatest civilizations. Their understanding of the stars allowed them to master the seasons and transform the desert into a living landscape. The Mayans built entire cities around seasonal alignments of light and shadow. In the ancient Maya world, architecture was astronomy. Temples and pyramids were designed so that sunlight would strike them in specific ways during solstices and equinoxes. At Chichen Itzá, the pyramid of Kukulkan transforms each equinox when sunlight and shadow combine to create the illusion of a serpent slithering down its staircase. Similar alignments appear in other Mayan cities, marking the agricultural calendar and religious festivals. These displays were not decoration, but precise measurements of the sun's journey. They reflected a worldview in which time, nature, and divinity were one. Every beam of light across a carved stone was a message from the cosmos, telling the people when to plant, harvest, and celebrate. The city itself became a living calendar, its walls and angles tuned to the same celestial rhythm that governs the turning of the seasons. The Inca Inti Raymi festival celebrated the sun's return after the winter solstice. High in the Andes, the Inca Empire honored the sun as the source of life. Each June, when the shortest day passed and the sun began its slow climb northward again, the people gathered in Cusco for the festival of Inti Raymi. Offerings of corn, gold, and llamas were made to thank the sun for its return. Fires were extinguished before dawn and reignited with sunlight reflected from mirrors, symbolizing renewal. The celebration marked the moment when darkness yielded to light and the agricultural season could begin anew. Even today, descendants of the Inca still perform the ceremony each year, a cultural echo of ancient astronomy. The festival stands as one of humanity's oldest expressions of hope, the recognition that every winter eventually ends and the light always comes back. The length of seasons changes over tens of thousands of years as Earth's orbit slowly shifts. Earth's path around the sun is not fixed. Over long timescales, gravitational influences from other planets cause the orbit to stretch and tilt slightly, altering how sunlight distributes across the globe. These subtle variations, known as orbital eccentricity, can make one hemisphere's summers longer and milder, while the others become shorter and hotter. The full cycle takes about 100,000 years. During these shifts, the contrast between seasons can either intensify or weaken, influencing glacial periods and climate stability. The mechanism operates too slowly for human senses, yet it shapes entire epochs. Our planet's long dance through space means that even time itself has seasons, vast cycles that determine when ice will spread, when forests will grow, and when the world will warm again. That slow shift is part of the Milankovitch cycles that shape ice ages. Serbian scientist Milutin Milankovic discovered that 3 major orbital patterns govern Earth's long-term climate: the tilt of its axis, the wobble of its rotation, and the shape of its orbit. Together, these cycles alter how much sunlight reaches different latitudes over tens of thousands of years. When they align to reduce summer warmth, ice sheets expand, beginning an ice age. When they shift the other way, glaciers retreat and interglacial warmth returns. Geological evidence from ocean sediments and ice cores confirms these periodic swings. The Milankovitch cycles are a reminder that the seasons we know are just one layer of a much deeper rhythm, a cosmic timetable spanning millennia. Every snowflake and summer breeze carries a trace of these grand celestial harmonies that have guided Earth's climate since time began. The southern hemisphere's seasons are milder because it has more ocean than land. Water moderates temperature. In the southern hemisphere, vast oceans absorb heat slowly and release it gradually, preventing the extremes of hot and cold seen in the north. As a result, summers in places like Australia and South America are generally cooler, while winters are milder. The ocean acts as a giant thermal buffer, evening out fluctuations across the year. The northern hemisphere, by contrast, contains most of the planet's landmass, which heats and cools quickly. This imbalance means that while both hemispheres share the same tilt-driven seasons, they feel them differently. The global pattern of land and sea determines not only regional weather, but also the emotional tone of the world's climates, gentler in the south, sharper in the north, all synchronized to the turning of the Earth beneath the baraff. Some. The northern hemisphere heats and cools faster because of its continents. Land responds to sunlight more dramatically than water. Because most of the planet's continents lie north of the equator, seasonal changes happen more abruptly there. In summer, the ground heats rapidly, raising air temperatures and creating strong weather systems. In winter, the same land loses heat quickly, allowing cold air to dominate. The oceans of the southern hemisphere act as stabilizers, but the land-heavy north experiences sharper contrasts. This difference influences everything from monsoon patterns to the strength of jet streams. It even affects the global balance of carbon dioxide, as vegetation in the north grows and decays in stronger annual pulses. The continents act like amplifiers in the symphony of the seasons, giving the northern half of the world its dramatic swings between green abundance and frozen stillness. Earth's elliptical orbit means one hemisphere's summer is slightly longer than the others. Earth does not circle the sun in a perfect circle, but in an ellipse. Because of this, it moves faster when it is closer to the sun, and slower when it is farther away. Currently, Earth reaches its closest point in early January, during the northern hemisphere's winter. This means that northern winters are shorter and milder, while southern summers, occurring when Earth is farthest from the sun, last a little longer, but are slightly cooler. The difference is small but measurable, about a week across the year. Over thousands of years, gravitational tugs from other planets slowly shift the orientation of this ellipse, changing which hemisphere enjoys the longer season. Even the length of summer is part of a cosmic rhythm, adjusted by the gentle physics of planetary motion. Summer in the northern hemisphere lasts about 4 days longer than summer in the south. Right now, the shape of Earth's orbit gives the northern hemisphere a small seasonal bonus. Because the planet moves more slowly in its distant part of the orbit, the stretch of time from the June solstice to the September equinox lasts about 4 days longer than the corresponding summer in the south. This difference affects ocean temperatures, monsoon timing, and even patterns of vegetation growth. Though barely noticeable day to day, it contributes to the broader climate balance between hemispheres. Over many thousands of years, this relationship will reverse as the planet's orbit shifts again. The unequal lengths of summer and winter are reminders that even the most familiar rhythms, the rising of heat, the fall of snow, are shaped by the subtle geometry of a world in motion. Seasons are opposite across the equator but linked by the same tilt. When it is summer in the north, it is winter in the south. Yet both hemispheres are responding to the same cosmic rhythm. Earth's axis remains tilted in one fixed direction as it orbits the sun, so when one side leans toward the light, the other leans away. The two hemispheres exchange roles every 6 months, trading warmth and cold in a balance that keeps the planet's total climate stable. The equator serves as the invisible line between these worlds, where sunlight remains nearly constant year-round. From space, this symmetry looks like a slow pulse of brightness shifting north and south through the seasons. Every storm, current, and gust of wind is part of this great oscillation. The hemispheres are not opposites but partners in motion, two halves of a single world turning gently under the same golden star. Migrating animals that cross the equator experience opposite seasonal signals. The species that migrate between hemispheres, time itself seems to reverse. Birds, whales, and even some butterflies follow long routes that carry them across the equator, passing from one set of seasons into another. As they move, the cues that guided them, daylight length, temperature, food availability, change direction. Yet evolution has equipped them to interpret these differences with extraordinary precision. Some whales feed in the cold, nutrient-rich waters of the Arctic or Antarctic during one hemisphere's summer, then journey to tropical seas to breed in the other hemisphere's warmth. Certain seabirds perform similar journeys, chasing continuous daylight across the globe. These migrations create a living bridge between north and south, linking two halves of Earth's seasonal cycle through movement. Each traveler experiences the full spectrum of the planet's rhythm: light, dark, warmth, and cold, all within a single year. Some cultures near the equator celebrate up to 6 microseasons tied to rainfall and harvest. In equatorial regions where sunlight hardly changes throughout the year, people have long measured time by subtler rhythms. Instead of 4 seasons, they recognize many, some as brief as a few weeks. These microseasons are defined not by temperature, but by rainfall, wind, or the ripening of particular plants. In East Africa, fishermen mark seasons by the arrival of monsoon winds. In parts of Indonesia, farmers speak of dozens of transitional periods, each guiding specific crops or rituals. The Japanese once named 72 such divisions, describing delicate shifts like frogs start singing or dew glistens on grass. Near the equator, nature's pace feels continuous rather than divided, yet communities still sense its subtle beats. Each microseason represents deep attention to the landscape, a calendar written in scent, sound, and sky. These traditions remind us that the Earth's clock has more than one way to tick. In Japan, the calendar divides the year into 72 subtle seasonal changes. Japan's traditional calendar, known as the Shichijuni-ko, divides the year not into 4 seasons, but 72, each lasting about 5 days. These miniature seasons describe nature's tiniest transitions, moments like east wind melts the ice, frogs begin singing, or bamboo shoots sprout. Rooted in ancient Chinese observation and refined by Japanese culture, The system celebrates fleeting beauty rather than fixed dates. It invites people to notice the smallest details of their surroundings: a shift in birdsong, the first scent of plum blossoms, the deepening color of rice fields. Although modern Japan now follows the solar calendar, these poetic intervals still appear in almanacs and art. They serve as gentle reminders to look closely, to witness the living conversation between weather, plants, and light. The 72 seasons express time not as something to measure, but as something to feel. Australia's indigenous calendars often track plant and animal behavior instead of temperature. Across Australia, indigenous peoples have maintained calendars that reflect the complex interplay of ecosystems, rather than simple divisions of months or temperature. Each region defines its own seasons according to natural signs: the blooming of certain flowers, the return of migratory birds, or the breeding of specific fish. In northern Arnhem Land, the Yolngu people recognize 6 seasons, including one marked by the arrival of dragonflies and another by the ripening of bush plums. In the desert interior, the Pitjantjatjara people track seasonal winds and seed cycles instead. These systems are not merely practical, they are deeply ecological, rooted in thousands of years of close observation. They teach when to hunt, gather, and rest, a living calendar written into the land itself. Even in modern Australia, these indigenous frameworks remain some of the most accurate measures of seasonal change. In Finland, the long twilight between seasons has its own name and festivals. In the northern latitudes of Finland, the transitions between seasons are drawn out into long, luminous twilights. Spring lingers in pale evenings that never quite darken, while autumn fades in slow, golden light. This in-between time is called ruska, a word that describes both the turning of leaves and the gentle melancholy that comes with change. Festivals celebrate the moment when daylight begins to vanish or return, and people gather outdoors to savor the sky's lingering glow. In midsummer, the sun barely sets at all, creating a season of perpetual dusk. In winter, the opposite occurs: a short, dim arc of light across the horizon, followed by endless night. The Finnish ear breathes in light and exhales darkness with unmatched subtlety, turning even the quiet hours of transition into occasions for wonder and reflection. The spring equinox can fall on different dates depending on your time zone. The equinox is a single moment, the instant when the sun's center crosses the celestial equator. But on Earth, it does not occur everywhere at once. Because time zones divide the planet into 24 slices, that moment may arrive on March 19th in one region and March 20th or 21st in another. The difference has nothing to do with the sun's movement itself, but with how humans divide time. As the planet spins, the precise crossing passes from east to west, like a wave of balance sweeping around the globe. Astronomers measure it down to the second, while most of us simply feel the lengthening day. Whether it arrives before sunrise or after dusk, the event is universal, the point where light and dark stand briefly equal before parting ways again. The Antarctic Peninsula has warmed enough to create a brief green season. In one of the most dramatic signs of climate change, parts of the Antarctic Peninsula now experience a fleeting season of green. During the short polar summer, rising temperatures melt snow and reveal patches of soil where mosses and algae take hold. These plants form bright carpets that glow against the ice, feeding on meltwater and sunlight for just a few weeks before freezing returns. Scientists studying these ecosystems call them the continent's green lungs, tiny oases of photosynthesis at the edge of the coldest place on Earth. The growth is a vivid symbol of transformation, life finding opportunity in change, yet also a warning of how fragile the balance remains. The appearance of green on the white continent marks a new chapter in Earth's story, one written in the language of shifting seasons and warming skies. Some Antarctic mosses survive 10 months of darkness by storing sunlight energy. In the harsh Antarctic winter, when temperatures plunge and darkness reigns for months, some mosses endure by banking energy during the brief summer. Their cells store sugars and protective compounds that prevent freezing, allowing them to survive even when frozen solid. During the dark season, metabolic activity nearly stops, but the structure of the plant remains intact. When sunlight finally returns, they resume photosynthesis almost instantly, as if waking from suspended animation. Scientists have found that these mosses can survive 10 months without light or liquid water, making them some of the hardiest plants on Earth. Their resilience offers clues about how life might endure on icy worlds beyond our planet. Each year, they demonstrate that survival is not only about endurance, but about knowing when to wait and when to grow. The tilt of Mars changes dramatically over millions of years, transforming its climate. Unlike Earth, Mars lacks a large moon to stabilize its tilt. As a result, the angle of its axis can vary wildly, sometimes nearly upright, at other times tilting more than 40 degrees. Over millions of years, these shifts have profoundly altered the Martian climate. When the tilt increases, sunlight reaches the poles more directly, melting frozen carbon dioxide and releasing it into the atmosphere, creating temporary warming. When the tilt decreases, the poles refreeze, and the planet becomes colder and drier. Evidence of these cycles lies in layered polar ice, each band marking a different epoch of tilt and temperature. The changing angle of sunlight has shaped the planet's winds, dust storms, and even the potential for liquid water in its past. Mars, like Earth, has its own deep rhythm of seasons written in time far longer than any human measure. Mars's thin atmosphere means its seasons are far colder than Earth's. Though Mars shares a similar axial tilt with Earth, its atmosphere is so thin that heat escapes almost instantly into space. As a result, even at the height of summer, temperatures can remain well below freezing. The thin air cannot hold moisture or buffer extremes, so the difference between day and night can exceed 100 degrees. Frost forms each morning from frozen carbon dioxide, not water, and melts away by midday. Seasonal winds sweep fine dust across the planet, painting the landscape in shifting shades of red and gold. At the poles, carbon dioxide snow falls each winter and sublimates in spring, driving enormous pressure changes that create global dust storms. The Martian seasons show what happens when sunlight shines on a world without air, beauty without warmth, rhythm without comfort, motion in near silence. Jupiter's tiny tilt gives it barely noticeable seasons. Jupiter spins almost upright relative to its orbit, tilting only about 3 degrees compared to Earth's 23. This near vertical orientation means that sunlight distribution changes little over the course of its 12-year orbit. As a result, the giant planet's seasons are nearly indistinguishable. Yet Jupiter's atmosphere remains dynamic for other reasons. Internal heat escaping from its core drives constant turbulence, forming the planet's famous belts and storms. The Great Red Spot, larger than Earth itself, has raged for centuries, fueled not by seasonal sunlight, but by deep convection within. Though Jupiter lacks the variety of seasonal change familiar to us, it displays ceaseless movement, a reminder that even worlds without tilt can remain in perpetual motion, their climates governed by forces far below their bright, clouded skies. Saturn's seasons last about 7 Earth years each. Because Saturn takes nearly 30 Earth years to complete one orbit of the Sun, each of its 4 seasons lasts roughly 7 years. As the planet tilts at an angle similar to Earth's, sunlight shifts slowly from one hemisphere to the other, changing the appearance of its atmosphere and rings. When a Saturnian summer begins, the clouds of the lit hemisphere brighten and the bands of color shift in tone. The rings, composed of ice and dust, reflect sunlight differently as the angle changes, creating subtle variations in their brilliance. Scientists studying these long seasons must wait decades to witness a full cycle. Saturn's year reminds us how relative time can be, how what seems short to us may unfold across an entire human lifetime elsewhere in the solar system. The tilt of Saturn makes its rings appear John only once every 15 years. As Saturn orbits the Sun, its tilt causes the rings to change their apparent angle when viewed from Earth. Twice during each 30-year orbit, they align perfectly John, becoming nearly invisible through telescopes. These moments occur when the Sun and Earth cross Saturn's equatorial plane simultaneously. When that happens, the thin rings, only tens of meters thick despite spanning hundreds of thousands of kilometers, vanish into a faint line of light. Observing these events helps scientists study the ring's structure and the small moons embedded within them. As the tilt continues, the rings gradually open again, revealing their full grandeur. This slow oscillation gives Saturn an elegant rhythm, as if the planet were bowing toward and away from the Sun in a cosmic dance that repeats every 15 years. Uranus rotates almost sideways, giving it 42-year-long seasons of light or dark. Uranus is unlike any other planet in the solar system. Its axis is tilted more than 90 degrees, meaning it essentially rolls around the Sun on its side. This extreme tilt creates seasons that last for decades. The 42 Earth years, one pole faces the Sun in continuous daylight, while the other lies in total darkness. Then the situation reverses. The long exposure to sunlight heats the atmosphere unevenly, producing dramatic shifts in cloud patterns and storms when the equinox arrives. From Uranus's perspective, sunrise and sunset are events of geologic duration. The planet's strange orientation may be the result of a colossal collision early in its history. Whatever the cause, its sideways spin makes it a world of deep contrasts, half glowing blue in light, half hidden in shadow, both waiting for the slow return of balance. Neptune's seasons last for decades because its year is 165 Earth years long. Neptune, the most distant planet, takes 165 Earth years to complete a single orbit of the Sun. With an axial tilt of about 28 degrees, it experiences distinct seasons, but each lasts over 40 Earth years. Since the invention of telescopes, humanity has observed only a handful of these transitions. Changes in the planet's methane clouds and winds reveal which hemisphere is receiving more sunlight. The shifting brightness of Neptune's atmosphere tells scientists when one season is ending and another beginning. Because sunlight there is 900 times weaker than on Earth, these changes unfold slowly, almost imperceptibly. Time moves differently so far from the Sun. A single Neptunian spring could span multiple human generations, a reminder that seasons are not just local phenomena, but cosmic rhythms echoing through the solar system. Even Pluto has seasons that change its thin atmosphere into frost and back. Despite its distance and size, Pluto experiences a surprisingly active seasonal cycle. When it approaches the Sun, its frozen surface of nitrogen and methane begins to sublimate, forming a thin, temporary atmosphere. As it moves away again, temperatures plummet and the gases refreeze onto the ground as frost. This process takes decades, synchronized with Pluto's 248-year orbit. Subtle color variations across its plains and mountains reveal where these seasonal exchanges occur. Spacecraft observations show haze layers rising miles above the surface, glowing faintly in sunlight before collapsing as winter deepens. Pluto's distant seasons remind us that even the coldest, smallest worlds still breathe, exhaling vapor and drawing it back again in rhythms too vast for a single lifetime to witness. The same tilt and light that shape Earth's spring and autumn reach even here, at the frozen edge of the Sun's domain. Some exoplanets experience seasons that last centuries. Beyond our solar system, worlds orbiting other stars display seasons beyond imagination. Some have orbits so elongated that one side of the year brings blistering heat, while the other plunges into centuries of cold. Planets circling dim red dwarfs may receive irregular bursts of warmth from stellar flares, producing unpredictable climate shifts. Others locked in slow, wide orbits experience gradual changes over hundreds of years, their seasons unfolding too slowly for any single generation of life to witness. On such worlds, spring could last longer than the entire history of human civilization. Astronomers detect these patterns by studying subtle changes in brightness or atmospheric composition over time. These distant climates reveal how diverse the universe can be, how the simple tilt and orbits that give Earth its gentle rhythm can, elsewhere, create extremes that stretch the meaning of a season itself. The color of distant planets can shift seasonally as clouds and ices move. Even from light years away, astronomers can sometimes detect the changing hues of alien worlds. As exoplanets orbit their stars, variations in reflected light reveal how clouds, storms, or surface ices shift with the seasons. A world covered in methane frost may brighten as it freezes and dim as it thaws. Others display color changes as dust storms sweep across continents, or as oceans reflect different angles of starlight. These patterns help scientists infer the presence of atmospheres, weather, and even oceans. Observations of Neptune and Mars show similar color shifts within our own solar system, teaching us how to interpret these distant signs. Each changing tint in the light from a faraway planet may be the signature of its own seasonal rhythm, a silent pulse of transformation echoing across the darkness between stars. Earth's seasonal carbon cycle can be seen from space as forests green and fade. From orbit, satellites observe the planet breathing. Each spring, as sunlight strengthens in the northern hemisphere, forests burst into life, absorbing carbon dioxide from the atmosphere. This vast photosynthetic surge lowers global carbon levels by measurable amounts. In autumn, as leaves fall and decay, that carbon returns to the air. The effect is so large that it forms a visible pulse in data collected by spacecraft, a planetary heartbeat synchronized with the seasons. In the southern hemisphere, smaller land masses produce a subtler rhythm, balancing the global average. This annual carbon exchange demonstrates how intimately the planet's atmosphere is tied to life. Every shade of green on Earth contributes to the cycle, each leaf playing a role in regulating climate. From space, the changing colors of continents tell the story of a living world inhaling and exhaling with the turning of the year. The northern hemisphere's forests cause measurable dips in atmospheric carbon dioxide every summer. Each summer, as sunlight pours across the northern hemisphere, the world's forests inhale. Trillions of leaves open their pores to the air, drawing in carbon dioxide and using its carbon to build sugars and cellulose. The process is so immense that satellites can measure the difference, a steady drop in atmospheric carbon levels from May through August. By late autumn, as leaves fall and decay, the gas returns, completing a global exhalation. Because most of Earth's landmass and vegetation lie north of the equator, this half of the planet dominates the carbon rhythm. The entire atmosphere participates in this living cycle, its composition rising and falling by measurable parts per million each year. These gentle fluctuations are the pulse of photosynthesis on a planetary scale, proof that forests breathe with the same precision as hearts or lungs, keeping Earth's air balanced for life. Every spring, plankton blooms in oceans absorb billions of tons of carbon. As sunlight returns to high latitudes each spring, the upper layers of the ocean awaken. Cold water, newly mixed by winter storms, holds nutrients that fuel an explosion of microscopic life. Phytoplankton, tiny algae floating near the surface, multiply by the trillions, turning entire swaths of ocean a faint green from space. Through photosynthesis, they absorb immense quantities of carbon dioxide, drawing it from the atmosphere into the sea. Some of this carbon sinks when the plankton die, locking it away in deep currents for centuries. These seasonal blooms are among the planet's greatest carbon regulators, rivaling forests in their effect on climate. They also sustain marine food webs, feeding everything from krill to whales. The ocean's springtime bloom is invisible from shore, but it is one of the most powerful expressions of life on Earth, a vast breath that cools the planet. In autumn, decaying leaves release that carbon back into the air. The crisp air of autumn carries the scent of transformation. As trees shed their leaves, the carbon captured through summer begins to return to the atmosphere. Fungi, bacteria, and insects break down the fallen matter, releasing carbon dioxide through respiration. This slow exhalation balances the inhalation of spring, forming a perfect seasonal loop. Some of the carbon lingers in soil, stored in humus that enriches future growth, while the rest drifts skyward, joining the air again. The cycle has continued unbroken for millions of years, powering forests, soil, and climate alike. Every glowing pile of leaves is a small part of a planetary process, the renewal of nutrients and energy through decay. What seems like an ending is actually the start of another turn in the global rhythm, as the Earth quietly exhales before preparing to breathe in once more. The tilt of the planet even affects how satellites generate solar power through the year. Earth's tilt not only creates seasons on the ground, but also changes how spacecraft experience sunlight in orbit. Satellites that rely on solar panels receive different intensities of light depending on the time of year and their position relative to the sun. Near the solstices, some spend longer in Earth's shadow, reducing the power available for instruments and communication. Engineers plan for these variations by adjusting battery cycles and scheduling operations during periods of maximum sunlight. The geometry of the seasons even affects satellites around other planets, such as Mars, where changing sunlight angles can cause panels to gather dust or lose efficiency. Every orbiting machine must adapt to the same cosmic mechanics that govern spring and winter below. The dance of tilt and light reaches far beyond Earth's surface, a celestial rhythm shaping the technology that watches over us from above. Spacecraft bound for Mars must launch in certain seasons for proper alignment. Sending a spacecraft to another planet is an exercise in celestial timing. Earth and Mars orbit the Sun at different speeds, so mission planners must wait for a window when the two worlds line up just right, an event that occurs roughly every 26 months. Launch too early or too late, and the journey would require far more fuel. These windows tend to fall in repeating patterns, forming a kind of interplanetary season known as a launch opportunity. Engineers calculate these alignments years in advance, aiming spacecraft so that both planets and sunlight cooperate perfectly. Even robotic explorers like the Mars rovers owe their timing to the geometry of the seasons. Across millions of kilometers, the same laws that bring spring to Earth also determine when a machine can leave home and begin its voyage through the solar system's shifting clockwork. Even the International Space Station has seasonal lighting patterns depending on its orbit. Orbiting Earth every 90 minutes, the International Space Station experiences 16 sunrises and sunsets per day. Yet across the year, the length and angle of these periods subtly change. As Earth tilts through its seasonal cycle, the station's orbital path alternates between longer stretches of sunlight and longer intervals of darkness. These fluctuations affect temperature, energy production, and even the circadian rhythms of astronauts. In summer months, certain orbits bathe the station in nearly continuous light, while in winter, it spends more time in Earth's shadow. To counter fatigue, the station's interior lighting is programmed to mimic a steady day-night rhythm. Though far above the weather, the ISS still lives within the same celestial pattern as every life form below. Even in orbit, the passing of the seasons can be felt in brightness, warmth, and the turning of light around the planet. Seasonal temperature swings shape patterns of disease, agriculture, and migration. The changing temperature of each season reshapes the behavior of nearly every species, humans included. Mosquitoes thrive in summer warmth, spreading malaria and dengue where temperatures allow frost halts them in winter. Crops grow only within certain thermal ranges, dictating harvests that have guided human civilization for 10,000 years. Animal migrations follow similar cues, birds flying toward warmth, mammals tracking vegetation, whales pursuing blooms of plankton. Even human diseases follow these same waves, rising and falling as conditions change. The Earth's seasonal heartbeat determines when food grows, when animals move, and when pathogens flourish. Scientists now track these cycles with global precision, mapping how the tilt of the planet shapes the health of ecosystems and societies alike. From farm fields to forests, from bacteria to elephants, all of life obeys the slow, steady rhythm of temperature and time. The timing of allergy seasons is shifting as global temperatures rise. Pollen counts now rise earlier in spring and linger longer into autumn. Warming temperatures extend the growing season for many plants, especially those that produce allergenic pollen such as ragweed, birch, and grasses. Studies show that higher carbon dioxide levels also increase pollen production, intensifying symptoms for millions of people. In some regions, allergy seasons now last several weeks longer than they did half a century ago. Shifts in rainfall and frost patterns compound the effect, altering where plants grow and when they release pollen. This subtle change in timing carries widespread consequences for health systems, agriculture, and the daily comfort of those sensitive to airborne particles. The drifting of seasons once meant renewal, now it also brings unpredictability. Even microscopic grains carried on the wind have become messengers of a changing climate. In cities, heat stored in concrete blurs traditional seasonal boundaries. Urban areas experience their own microclimates. Pavement, brick, and glass absorb sunlight during the day and release it slowly at night, creating what scientists call the urban heat island effect. This constant warmth can raise local temperatures by several degrees compared to surrounding countryside, muting the sharp transitions between seasons. Snow melts faster, frost arrives later, and plants bud earlier along city streets. Birds alter their migration schedules, and insects survive winters that would once have killed them. Buildings and traffic add more heat, reinforcing the effect. In some metropolises, summer now stretches far longer than nature intended. As global warming amplifies the phenomenon, cities become laboratories for studying how climate and infrastructure interact. The result is a world where the familiar rhythm of seasons blurs, replaced by a new, human-made tempo of light, heat, and stone. Snowfall patterns are moving northward at about 50 kilometers per decade. Over the past half-century, satellite records have revealed a gradual migration of snowfall zones. Warmer temperatures cause winter precipitation to fall as rain in regions that once saw snow, pushing consistent snowlines farther toward the poles and higher up mountain slopes. The shift averages roughly 50 kilometers per decade in the Northern Hemisphere. This movement affects water supplies, ecosystems, and winter sports industries alike. Snowpack serves as a natural reservoir, melting slowly to feed rivers in spring as it retreats. Downstream regions face droughts and altered growing seasons. The timing of snowmelt also changes, arriving weeks earlier than it once did. Each flake still forms through the same physics of freezing vapor, but the geography of where it falls is rewriting climate maps. Snow, once a symbol of permanence, is now a moving frontier. Climate scientists track the start of spring using satellite data on vegetation. Modern technology can see spring arrive from space. Using sensors that detect subtle changes in color and light reflection, satellites monitor the greening of vegetation across continents. Scientists measure a parameter called the Normalized Difference Vegetation Index, which increases as plants begin photosynthesis. By analyzing decades of data, researchers can determine the precise day that growth starts each year, and they've found that spring is coming earlier across most of the northern hemisphere. The shift, often by several days or weeks, affects everything from agriculture to animal migration. The global view reveals how interconnected the planet's ecosystems are. A single change in temperature or daylight can alter timing across thousands of miles. The first blush of green captured from orbit marks not just a change of season, but the living pulse of the biosphere itself. Some migratory birds are now arriving weeks earlier than they did 50 years ago. Long-term studies of bird migrations show that many species now reach their breeding grounds far earlier than they once did. As springs warm sooner, insects hatch earlier and plants flower ahead of schedule, prompting birds to adjust their journeys. Some species, such as swallows and warblers, have advanced their arrival times by more than 2 weeks in recent decades. Yet not all can keep pace with the shifting climate. Birds that migrate long distances, relying on daylight cues rather than local temperature, often arrive too late to feed their young on peak insect populations. The result can be population declines and disrupted ecosystems. Migration, once synchronized with the steady rhythm of the seasons, now races against a changing clock. The sky's great travelers are adapting in real time, their flight paths tracing the evolving heartbeat of the planet. The Arctic is warming 4 times faster than the global average, altering its seasons entirely. In the far north, the rhythm of the year has accelerated beyond recognition. Temperatures in the Arctic are rising at roughly 4 times the global average, shortening winters and lengthening the thaw. Sea ice forms later, melts earlier, and covers less area each year. Permafrost that has remained frozen for millennia now softens, releasing methane and reshaping the land. Animals such as caribou, polar bears, and Arctic foxes struggle to adapt as food sources shift and breeding seasons desynchronize. Indigenous communities face collapsing ice roads and unpredictable weather that undermines traditional hunting patterns. What was once a region defined by steady cycles of light and dark is becoming a place of constant change. The Arctic's transformation is not isolated, it ripples outward, influencing ocean currents and weather systems across the globe. Polar night is shrinking as sea ice disappears sooner each year. The long darkness of the Arctic winter, known as the polar night, is beginning to shorten. As sea ice melts earlier in the year, open water absorbs more sunlight, storing heat that lingers into autumn. This delays the formation of new ice and extends twilight farther into what was once unbroken night. Satellites now detect measurable changes in how long the polar regions remain dark. For the creatures that depend on this rhythm, seals, krill, and plankton, the shifting light alters feeding and reproduction cycles. Some scientists refer to this as the blue twilight era of the Arctic, a new intermediate state between dark and light. The fading of the polar night marks another way the seasons are being rewritten, not by celestial mechanics, but by human influence reshaping the most ancient rhythms of the world. Seasonal ice melt now exposes ancient landscapes unseen for tens of thousands of years. As glaciers and ice sheets retreat, they uncover terrains that have been hidden since before human civilization began. In Greenland and Antarctica, scientists have discovered moss, soil, and even ancient riverbeds beneath the thawing ice, preserved in suspended time. Radiocarbon dating shows that some surfaces were last exposed more than 100,000 years ago. These landscapes provide a glimpse into Earth's climate before the last ice age, but their re-emergence comes at a cost. Meltwater from these regions contributes to rising sea levels, and the ecosystems once entombed in ice face exposure to erosion and microbes. Each summer's melt reveals new secrets of the planet's past while rewriting its future. The thaw is both revelation and warning, showing how quickly even the most permanent parts of the world can change. Scientists can date old ice layers by counting annual melt and freeze lines. Deep within glaciers, each year leaves behind a delicate signature, a layer formed during the summer melt and another from the winter freeze. These alternating bands trap tiny bubbles of air, pollen, and volcanic dust, preserving a record of Earth's atmosphere through time. By drilling ice cores and counting the layers, scientists can determine not only age, but also temperature and greenhouse gas levels stretching back hundreds of thousands of years. The oldest continuous core from Antarctica reveals climate patterns over 800,000 years. Each line represents one revolution of the planet around the sun, one cycle of the seasons. In the language of ice, time becomes visible, a frozen diary of how sunlight, air, and life have changed together. The Earth's memory, it turns out, is written not in words, but in layers of frozen light. Each tree ring marks a full sequence of the 4 seasons. Inside every tree trunk lies a record of its life. Each ring corresponds to 1 year, beginning with light, wide growth during spring and summer, followed by darker, denser wood formed in autumn and winter. The pattern repeats endlessly, allowing scientists to read not just a tree's age, but its history. Years of drought, frost, or abundant rain appear as subtle variations in thickness and color. By comparing overlapping tree rings from different generations, researchers can reconstruct climate conditions stretching back thousands of years. Forests, in this sense, are libraries of time, each tree a living chronicle of sunlight and season. Even after a tree falls, its rings preserve the rhythm of its years. Countless cycles of growth and rest, each one the imprint of the earth turning once more beneath the changing sky. Coral skeletons record seasonal ocean temperatures year by year. Beneath the waves, corals build limestone skeletons that grow layer by layer, forming bands much like tree rings. Each layer reflects the chemistry of the seawater at the time it formed, including temperature, salinity, and nutrient levels. Warm seasons produce lighter, less dense bands, while cooler months form darker ones. By drilling tiny cores from living corals, scientists can reconstruct seasonal changes in ocean climate over centuries. These records reveal patterns of El Niño events, monsoons, and long-term shifts in sea temperature. Coral archives complement ice cores and tree rings, extending our understanding of the planet's climate into the tropics. Each reef is both ecosystem and archive, a living memory bank of the ocean's changing mood. As reefs face modern stress from warming waters, their layered skeletons preserve the story of what the sea once was and what it may become. Even cave stalagmites contain annual bands that trace ancient rainy and dry seasons. Inside limestone caves, water dripping from above leaves behind thin layers of calcite, forming stalagmites that grow upward over thousands of years. Each layer records the chemical composition of the water that formed it, reflecting rainfall, temperature, and vegetation outside. During wet seasons, the layers form quickly in dry years, They grow slowly or stop entirely. By analyzing these bands and their isotopic makeup, scientists can reconstruct climate patterns long before written history. Some stalagmites in China, South America, and Europe preserve records stretching back 500,000 years, detailing the rise and fall of monsoons and droughts. Like tree rings and ice cores, they speak the same language of time, a rhythm of growth and rest, guided by the turning of the planet. In the silence of caves, the story of the seasons continues to form, drop by patient drop. Every heartbeat, breath, and harvest on Earth ultimately traces back to the slow rhythm of the seasons. The tilt of our planet governs far more than weather. It shapes the very conditions for life. Every organism, from coral polyp to human being, exists within the repeating cycle of light and dark, warmth and cold. Oceans circulate, forests breathe, and animals migrate to its rhythm. Civilizations rise by mastering its timing calendars, rituals, and agriculture, all began as responses to its pattern. Even our bodies carry traces of it, with hormones, moods, and sleep following the subtle changes in sunlight. The rhythm of the seasons is the planet's heartbeat, ancient, steady, and shared by all. To live on Earth is to move in harmony with this great cycle, each breath an echo of the same celestial turning that guides the tides, the flowers, and the stars. Somewhere high above, the Earth is still turning. Its axis leans softly, tracing an invisible rhythm through the heavens, a movement so subtle we forget that everything we know depends on it. Because of that tilt, snow melts and rivers flow. Flowers bloom, leaves fall, and oceans breathe in long, slow sighs. Every creature that has ever lived has measured its life against this same rhythm, the heartbeat of the seasons. Tonight, as you drift toward sleep, imagine the planet gliding through its orbit. Picture the sunlight shifting across oceans and continents, pulling dawn forward in one place and letting night settle in another. From this perspective, the year feels less like a calendar and more like a great circular wave, slow, steady, endless. Somewhere, a glacier is beginning to thaw. Somewhere else, ice is forming in its place. The balance holds, always changing, always returning. All around you, that rhythm continues. The air cools and warms, the stars wheel overhead, and life quietly adjusts. The trees outside your window sense the lengthening of night. Tiny seeds beneath the soil are already preparing for spring. Even your heartbeat, steady and calm, follows that same natural pulse, slowing as light fades, finding rest as the world tilts gently toward darkness. The seasons remind us that change is not something to resist, but something to trust. Each cycle carries both ending and renewal. The promise that warmth will follow cold, that morning will follow night. The Earth has kept this promise for billions of years, circling faithfully around its star. And as you lie here, breathing with the rhythm of the planet, you are part of that same unbroken pattern, a single note in the quiet music of time. So let the world keep turning without you for a while. Let the pull of the orbit and the hum of the seasons rock you gently into sleep. Tomorrow the sun will rise a fraction of a degree in a slightly different place, and the cycle will begin again, light lengthening somewhere, shadows deepening somewhere else. But for now, you can rest. The year will keep its rhythm. The Earth will keep its course. And the slow, beautiful turning of the seasons will go on, carrying you softly with it into dreams. Good night.